In this video, I'm going to make a question about rabbits as complicated as is humanly possible. Let's get to it. Fibonacci defined a certain sequence as such: 0 and 1 being the starting values, and then each successive value being the sum of the previous two values. And so the next one would be 0 plus 1 equals 1, 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5, 3 plus 5 equals 8, 5 plus 8 equals 13, and so forth. You get the idea. Anyway, this was used to model the spread of rabbits, which are famous for spreading quite rapidly. However, the problem with the sequence is that it's recursively defined. Basically, it's defined based on how on the terms that come before it, not necessarily its position in the sequence. We can't really easily find the 700th value of the sequence without going through 699 values before the 699 before that. Linear algebra, the study of matrices, however, offers a potential solution. Suppose we have the vector. By the way, I'm going to assume that you know how to diagonalize a matrix, and that you know stuff about eigenvalues and eigenvectors. If explaining that will make this into like a 40-minute video. So, and I would rather it not be a 40-minute video because my brother is doing a very good job of being the cameraman, and I don't want to make him wait for 40 minutes. So say we have a vector defined as this is the n plus 1th term in the sequence, and then this is the nth term in the sequence. First, we're going to want to find a matrix A, B, C, D, such that this is equal to A of n plus 2, A of n plus 1, which of course would be equal to A of n plus 1 plus A of n, then A of n minus 1 plus A of n. Or that would alternatively be, well, equal to A of n plus 1, A of n, then A of n plus 1. That would be a bit easier. So, using the rules for vector and matrix multiplication, we get A times A of n plus 1 plus B times A of n equals A of n plus 1 plus A of n. And when you know it, it's just A equals 1 and B equals 1. And now C times A of n plus 1 plus D times A of n is equal to A of n plus 1. We don't really even need this term. We can just make C equal 1. So this matrix here is 1, 1, 1, 0. And as you know, if you want to do this, so do the action again, we just square it. And if you want to do it however many times, you just take it to a power. And then we just multiply that by the starting term, which would be 1 and 0. Now, this is a little bit tricky to calculate. Let's say n is 100. This is really hard to multiply out. So we're going to want to diagonalize this so that it's easier to calculate. And just a reminder, diagonalization is putting it into this format. I'm going to turn this over to the other side. And to diagonalize it, we need to know the eigenvalues and the basis for the eigenvector of this matrix. So to find the eigenvalue, we find the characteristic equation, which would be the determinant of this matrix, where this is the eigenvalue. To find the determinant, we just find that times this minus this times this. That would be equal to squared minus. So we solve for, I can't remember if this is lambda or gamma. I need to work on Greek letters. And using the quadratic
I think that's
formula.
lambda.
Okay, thanks.
But I'm not sure.
Using the quadratic formula, we get this. And this here is so common in math that we have a special Greek letter for it, phi. And then this here, that's also pretty common in math, since we have another name for like phi prime. And so we know that E is going to be equal to phi, and F is going to be equal to phi prime. Now, to get A, B, C, D, we need to find the eigenvectors. And so to do that, we find the null space of this minus each of the eigenvalues times the identity matrix. That's going to be equal to 1 minus phi 1, and then 1, and then negative phi. So we know that times, let's say, GH is going to be equal to 0. And we don't necessarily need to find the exact values of G and H. You just need to find a basis for the null space. And so G and H are just going to be relative to each other. And I should probably put the 0 vector here. And so we know that G plus negative phi times H is going to be equal to 0. And so we know G equals phi of H, and let's make this easy. G equals phi, H equals 1. And now so the basis of the null space for phi is phi 1. Now, basis for the null space of this here you just go through the same process, and we get phi prime and 1. So we know that this matrix here is going to be equal to this here and this here. Now we just need to find the inverse. Can you pause this, Anthony, so I can get more paper?
Yep. So before you say any more, I just have to say I Googled it, and it turns out I was right. It's lambda.
Okay, so you know that this or n is equal to this here times this